All right, so we just looked at exponential growth. Now we're going to switch gears and look at exponential decay. And here's just a quick illustration of what that will look like. It'll be decreasing as you look at this from left to right. And it'll be a horizontal asymptote at y equals 0 or the x-axis. Some characteristics of this, and I highlighted the differences here as compared to exponential growth. So in this case, your k value will be negative, okay? So you can have a negative in the exponent position. That'll create the rapid decrease in the graph of the function. And k is now called the decay constant, the decay constant. All right, let's take a look at an example. So, phosphorus 32, P32, has a half-life of 14.2 days. If 750 grams of this substance, are present initially, find the amount present after T days. Determine the decay constant. What amount will be left after 30 days? Okay, so this is going to be handled very similarly as compared to the first example we did in this section. All right, so first thing is, let's set up an equation so we can solve for our decay constant K. All right, so we have 750 grams of this substance present initially. That's going to be our Q sub 0. Write this down here. All right. And then it says what? It's has a half-life of 14.2 days. Okay, so T is going to be 14.2, and half-life means that 1/2 of this will be gone after this period of time. So what's 1/2 of 750? 1/2 of 750 is 375. Okay, so note now in this example, Q of T is less than our initial quantity based upon a certain period of time. All right, so look, what will happen though when you divide both sides by the initial quantity is you're going to get 1/2 on the left. Okay, remember in the previous example we got 2 on the left. Look, if it's a half-life, you're going to get 1/2 here, I guarantee it. If it said doubling after a certain period of time, this would be a 2. If it said tripling, this would be a 3, and so on and so forth. This is the time required for 1/2 of something to be decayed, to be, done away with. All right. So now what do we do? The process is the same here, folks. You're going to do the natural logarithm of each side. And you get 14.2K on the right. That's the whole point. And then what do? To solve for K, we divide both sides by 14.2. So we get this over 14.2. If you wanted to approximate this out 4 decimal places, you would put the natural logarithm of 1/2 in your calculator and divide it by 14.2. And I believe you get the opposite of what? This, 488 10,000ths. Note that K is negative. All right, so that's the decay constant. We have that part taken care of. And then let's come up with the model. So Q of T is now equal to what? 750 times e to the k, which is this ln of 1/2 all over 14.2. This is all in the exponent position. There's our model, okay? This is our mathematical exponential what? Decay model, okay? So what amount will be left after 30 days? That's just simply Q of 30. All right, Q of 30. So Q of 30 is going to be equal to 750 e to the whatever this is. You know what? I'm just going to use this. It'll be a little bit quicker perhaps. And then times 30. And so you plug this in your calculator. And let's see what we get here. Let's plug this in our calculator. So let's see, 750. Then E is right here. E is right right on top of the ln button. So you have to hit second and then ln, and there's your E. And then we do what? Negative 0.0488 times 30, all in the exponent position. And then hit enter. So let's say about, well, to the nearest day, it'd be, or excuse me, to the nearest gram, to the nearest gram, it'd be 173 grams would be remaining, right? 173 grams would be remaining after 30 days of this particular substance. Just round to whatever WebAssign wants you to round to. Okay, that concludes example number 2. I think we have one more thing to look at here. One more example. All right, let's wrap up section 3.3, which is going to be, for us, wrapping up chapter 3, okay? There are other types of exponential functions out there. This is a learning curve. You will not have to derive this. You'll not have to come up with this model on your own, but you should be familiar with it. Really, all you're going to have to be able to do with this type of function is solve for whatever they want you to solve for. So you're going to have to solve for one of the variables based upon given information. And that could also be true with something like this as well. This is a logistic curve. Again, you will not have to formulate this, but you could be asked to solve for one of the variables, for example. Okay, let's take a look at our last example, section 3.3. Oh, this is sort of relevant, isn't it? Sort of relevant. Spread of an epidemic. Of course, we're in a pandemic. Anywho, during a flu epidemic, the number of children in the Woodbridge Community School system who contracted influenza after T days was given by this model. All right, this is a logistic model. Okay, so letter A, how many children were stricken by the flu after the first day? After the first day. Well, all you have to do is this. Q of 1. All right, so here you're not even solving for anything. You're just simplifying an expression. So that would be what? That'd be 1,000 all over 1 plus 199 times e to the negative what? 0.8 times 1. That's it. And then you'd get about what? Well, you'd plug that in your calculator. I'll go ahead and show you number 1 in the calculator here. So that's going to be, what here? That's going to be 1,000 divided by, and you could do this separately. You don't have to do it this way if you don't want to, but it is 1,000. And then divided by what? Divided by the quantity of 1 plus 199 times base e to the power of what? Negative 0.8 times 1, which is going to just be negative 0.8. But anyway, this is our expression. Hit enter. And so you see we get about 11 children. So just after 1 day, 11 children now have the flu. Okay, so what's going to happen then in letter B? How many children had the flu after 10 days? Well, let's see. After 10 days, all we're going to do is change the t from a 1 to a 10. So the expression's exactly the same. But now when we enter this into our calculator, this is going to be shocking. Just after 10 days, how many children have the flu? Run that through your calculator, see what you get. 937 children. So apparently this is why they want us to wear masks and stay 6 feet apart, et cetera, et cetera, et cetera. Fun times. Anyway, that wraps up section 3.3 and also what we're going to look at in chapter 3. Hope you're staying well and being safe and being good to one another. Take care. Bye-bye now. See you in class.